We have discussed so far different applications of large sample procedures in statistics. We have discussed Z transformation, that is Fisher's Z transformation, in our last module. In this module, we shall start with different applications of Z transformation regarding estimation, testing of hypothesis and confidence interval estimation of multiple bivariate normal populations. Then we pass on to our next topic, which is on frequency chi-square or Pearsonian chi-square. Actually, what we have discussed so far is related to asymptotic distributions regarding some discrete or continuous distributions. But often we get observations in terms of frequencies. So in such a case, we need to develop some other types of theory for large sample distributions. So we discuss all these things in this current module, and we shall next discuss few applications of Pearsonian chi-square and give some introductory and motivating examples on how to get better results using Pearsonian chi-square statistics. So in our last module, we have seen what is Z transformation and how to obtain such a transformation as a variance stabilization technique. And in this module, we start with use of Z transformation for single bivariate populations. That is, we shall discuss different inferential procedures using Z transformation. So suppose xi, yi are IID pairs of observations from a bivariate normal population with correlation coefficient rho, and of course here we are not discussing about the other parameters, and we assume that the other parameters are also unknown. Suppose first of all we want to test the null hypothesis that rho equal to rho naught for rho naught not equal to 0. Then we can use the statistic Tn, which is square root of n multiplied by tan hyperbolic inverse r minus tan hyperbolic inverse rho naught, which under the null hypothesis is asymptotically standard normal. Thus we reject the null hypothesis against the alternative that rho not equal to rho naught if the observed value of absolute value of Tn exceeds tau alpha by 2. Similarly, the one-sided hypothesis can also be considered. Again, for confidence interval estimation, we can use the quantity square root of n multiplied by tan hyperbolic inverse r minus tan hyperbolic inverse rho as a pivot, and can obtain a confidence interval with endpoints tan hyperbolic z1 and tan hyperbolic z2 with approximate confidence coefficient 1 minus alpha, where z1 is tan hyperbolic inverse r minus tau alpha by 2 divided by square root of n, and z2 as tan hyperbolic inverse r plus tau alpha by 2 by square root of n. It should be mentioned in this case that if our rho naught is 0, then one can perform a test for rho equal to 0, that is test for independence, using T statistic. So we have some alternative test and which is valid for every alternative rho naught. Next, consider some types of estimation. Suppose we have k independent samples from k bivariate normal populations with common correlation coefficient rho. Assume that ni observations are available from the ith population and ri is the sample correlation coefficient for the ith population. Suppose it is required to obtain a pooled estimate of rho, that is, we get information from k bivariate normal populations and the common correlation coefficient is rho. So definitely rho should be estimated considering all these samples together. So that is what is known as a pooled estimator of rho. So we define Zi as tan hyperbolic inverse Ri, then asymptotically it has a normal distribution with mean zeta, which is defined as tan hyperbolic inverse rho, and variance 1 by ni. Hence, considering the inverse variance as the weights, we get the pooled estimator of zeta as zeta hat, which is defined as the weighted mean summation I from 1 to k ni zi divided by summation I from 1 to k ni. Therefore, we have obtained an estimator of zeta, and since rho is an one-to-one function of zeta, we can get a pooled estimator of rho using the relation that rho hat is nothing but the tan hyperbolic inverse zeta hat. However, in actual practice, in some further computations, it has been shown by many researchers that it is better to replace Ni by Ni minus 3. Next, consider a test of homogeneity. As earlier, we have k independent samples from bivariate normal populations with different correlation coefficients. For example, we assume that the sample size for the ith population is Ni and the corresponding correlation coefficient of course in the population is rho I. Suppose we are interested in the homogeneity hypothesis, which is rho 1 equal to rho 2 up to equal to rho k. If Ri is the sample correlation coefficient for the ith population, then square root of Ni multiplied by Zi minus zeta I, where zeta I is nothing but tan hyperbolic inverse rho I, is asymptotically standard normal. Zeta naught is the common unspecified value under the null hypothesis. Then we may take our statistic Tn as summation I from 1 to k Ni minus 3 multiplied by Zi minus zeta naught whole square, which is approximately distributed as a chi-square with k degrees of freedom. However, zeta naught is not specified, and hence we replace it by pooled estimator zeta naught hat, which is summation I from 1 to k Ni minus 3 Zi divided by summation I from 1 to k Ni minus 3, that is weighted mean of Zi with weights being Ni minus 3. So we get our modified statistic Tn dash as summation I from 1 to k Ni minus 3 multiplied by Zi minus zeta naught hat whole square, that is just by plugging the zeta naught hat in the original estimator in our original statistic Tn. Since we have replaced zeta naught by zeta naught hat, therefore we get some linear restriction, and it is well known that the distribution of sum of squares subject to some linear restriction reduces the degrees of freedom of the chi-square variable, and since we have one linear restriction, we get the asymptotic distribution as chi-square k minus 1 as compared to the chi-square distribution with k degrees of freedom for Tn. Therefore, a large sample test would reject the null hypothesis if the observed value of Tn dash exceeds chi-square k minus 1 alpha. So finally, the same methods can be adopted for the homogeneity of k Bernoulli population or normal population with respect to variance or Poisson population. In addition, for k independent samples of different sizes from the same population, one can as earlier obtain pooled estimates of the parameters of interest. However, the subsequent development is routine and hence we skip the details. At this point, it should be noted that if we want to test the homogeneity of k normal population with respect to mean considering equal variances and unknown variances, then the procedure is nothing but one-way analysis of variance. So this should be kept in our mind that whenever we have data from several normal populations with equal variances, then we need not to adopt large sample procedures because a good small sample procedure is available. Next, we pass on to our next topic, which is on asymptotic distributions related to quadratic forms. So far actually we have discussed asymptotic distributions of some linear functions or some g function of this, but we have not used asymptotic techniques related to quadratic forms. So in this module we start with finding the asymptotic distribution considering some random quadratic forms. So note that often our test statistic comes in the form of a quadratic form. If the exact distribution of such a statistic is not tractable, asymptotic methods are the only options. For example, if we consider the quadratic form x transpose multiplied by some matrix A and then x, and if x has a normal distribution, then this quadratic form has a non-central chi-square distribution provided A satisfies some conditions for general distributions. If A is idempotent, then the purpose is served, or otherwise some function of A and sigma, that is dispersion matrix of X, has to be imposed. So for normal quadratic forms where X has some multivariate normal distributions, the exact distribution can be obtained. However, if the distribution of X in such a quadratic form differs from normality, the asymptotic distribution, even the exact distribution, is not tractable or even can be obtained. However, the asymptotic distribution of a quadratic form is not the usual normal, in fact chi-square. So what we have discussed so far, in most of the cases we find the asymptotic distribution as a normal, and in some cases some variation of this. But in this case, when the quantity is a quadratic form, we get a positively skewed distribution as our limiting distribution. In fact, we get some variations of chi-square distribution. Thus, we start with some basic asymptotic results on quadratic forms and later provide applications in statistical hypothesis testing. We start with some auxiliary results before we proceed to our general result of interest. So we start with lemma 1. If the p component vector X has a p-variate normal distribution with mean mu and dispersion matrix sigma, where dispersion matrix sigma is assumed to be positive definite, then the quadratic form Z, which is defined as X minus mu transpose sigma inverse multiplied by X minus mu, has a chi-square distribution with degrees of freedom p. The proof of the above result is very simple, but still we give some outline of this proof. Since sigma is positive definite, sigma inverse is also positive definite. So there exists a matrix C such that C multiplied by sigma inverse multiplied by C transpose is identity matrix of order P. Now if we define Y as C times X minus mu vector, then Y has a p-variate normal distribution with mean vector 0 and dispersion matrix IP. So using the relation that C is non-singular, we can express Z as Y transpose Y, which is nothing but summation I from 1 to p yi square. And since the distribution of Y vector is p-variate normal with mean 0 and dispersion matrix IP, different components of yi are IID as standard normal. Therefore, it follows from the definition of a chi-square variable that Z is the sum of squares of p independent chi-square 1 variables. Therefore, by definition, Z has a chi-square distribution with p degrees of freedom. Next, consider our next lemma. If xi are IID p component random vectors with mean mu and dispersion matrix sigma, and sigma is assumed positive definite, then W defined as n times x bar minus mu transpose Sn inverse multiplied by x bar minus mu converges in distribution to a chi-square distribution with p degrees of freedom, where Sn is the sample variance covariance matrix defined by 1 by n summation I from 1 to n xi minus x bar multiplied by xi minus x bar transpose. So for a proof, first of all we use multivariate CLT. Then since xi are different variables, different vectors which are IID, we can say that square root of n multiplied by x bar minus mu converges in distribution to some random variable y, where y has a p-variate distribution, p-variate normal distribution with mean vector 0 and dispersion matrix sigma. Since Sn can be expressed as 1 by n summation I from 1 to n xi transpose minus x bar transpose, and we have Slutsky's theorem, we get that 1 by n summation I from 1 to n xi transpose converges in probability to sigma plus mu transpose, and x bar transpose converges in probability to mu transpose, and therefore we get that Sn converges in probability to sigma. Hence, From Slutsky theorem, we get that W converges in probability to a random variable which is actually W converges in distribution to a random variable which is defined as y transpose sigma inverse y, and then applying lemma 1 as we have discussed earlier, we get the quantity y transpose sigma inverse y is distributed as a p-variate, as a chi-square distribution, as a chi-square variable with p degrees of freedom, and therefore we get the result. Our next topic, which is on Pearsonian chi-square statistic. So before we go to some application, let us form the statistic and the basic premises. Suppose n independent trials are performed. Each trial has k mutually exclusive and exhaustive outcomes a1, a2, ak, with pj as a probability for the jth outcome. Naturally, since we are considering mutually exclusive and exhaustive outcomes, sum over pj for every j is unity. Let fj be the number of trials with outcome aj, so that summation fj equal to n. Then Pearson's chi-square statistic is defined as Tn equal to summation I from 1 to k fj minus npj whole square, whole thing divided by n times pj. Now we just pass on to our next result, which states that as n tends to infinity, Tn converges in distribution to a chi-square variable with k minus 1 degrees of freedom. So for a proof, define the k component outcome vector for the ith trial x upper I, where the jth component of x upper I takes the value 1 with probability pj, and it takes the value 0 with probability 1 minus pj, so that exactly k minus 1 components of x upper I are zeros and only a single one, so that the sum summation j from 1 to k xj upper I equal to 1. Then x upper I for I equal to 1 to n are IID vectors with x upper I having a multinomial distribution with parameters n, p1 up to pk. So that then x upper I are IID vectors with x upper I having a multinomial distribution with parameters n, p1 up to pk, so that expected value of x upper I is p. P is a vector with components p1, p2, pk, and dispersion of x upper I is nothing but a matrix which is defined as diagonal matrix of diagonal matrix with diagonal elements p1, p2, pk minus p transpose. However, dispersion of x upper I is singular because of the fact that summation pj equal to 1, and hence we introduce a new variable y upper I, which is a k minus 1 component vector with components x1 upper I, x2 upper I, and xk minus 1 upper I. This vector is formed by k minus 1 components. Then y upper I are IID vectors with expected value as a vector with components p1, p2 up to pk minus 1, and dispersion matrix of y upper I is denoted by sigma, which comes out as a diagonal matrix with a diagonal elements p1, p2 up to pk minus 1 minus the product of two vectors with elements p1, p2, pk minus 1, and the another vector is also having the same elements p1, p2, pk minus 1. Now, since sigma is positive definite, it follows from multivariate CLT that Zn, which is defined as square root of n multiplied by y bar minus the vector with elements p1, p2 up to pk minus 1, converges in distribution to a k minus 1 variate normal distribution with mean vector 0 and dispersion matrix sigma. Hence, it follows from lemma 2 that Zn transpose sigma inverse Zn converges in distribution to a chi-square variable with k minus 1 degrees of freedom. Now, using some matrix algebra, one can find that sigma inverse can be expressed as the sum of two matrices. Now, using some matrix algebra, matrix inversion, one can find that sigma inverse can be expressed as the sum of two matrices. The first one is a diagonal matrix with elements 1 by p1, 1 by p2 up to 1 by pk minus 1, and the second one is another matrix 1 1 transpose divided by pk, where pk is defined as 1 minus summation I from 1 to k minus 1 pi. Then noting the fact that y bar equal to is nothing but a vector with components f1 by n, f2 by n up to fk minus 1 by n, and fk is defined as n minus summation I from 1 to k minus 1 fi. A simple algebra with quadratic form expresses the quadratic form Zn transpose sigma inverse Zn as Tn, and since the distribution, the large sample distribution of Zn transpose sigma inverse Zn is obtained as chi-square with k minus 1 degrees of freedom, therefore the large sample distribution of Tn is also chi-square with k minus 1 degrees of freedom, and this completes the proof. What are the applications of Pearson's chi-square statistic? So we have defined Pearson's chi-square statistic and obtained its large sample distribution. So let us just enumerate its application in statistics. So the first application is known as tests for goodness of fit. Often the underlying distribution of the data is not known, and traditional practice is to use normality, but such an assumption makes the inference weaker. Therefore, the experimenter wishes to know whether the underlying distribution is of a given form. That is, the objective is to know which distribution fits good to the observed data. Tests for determining the underlying distribution which is a good fit to the observed data are called goodness of fit tests. So we start with some motivating example. Suppose the number of misprints per page of a book of 300 pages are represented in the form of a grouped distribution. So we have the classes number of misprints per page, which is either 0, 1, 2, 3 or exceeding 4, and the corresponding number of pages are given in the presentation. Here one can find the number of observations, that is 300, is quite large to assume normality. But the variable is discrete with small number of categories. It is well known that the number of misprints per page has in general a Poisson distribution, but the mean, that is the only parameter for the Poisson distribution, is not specified in advance. Then how to test the hypothesis that the observations are coming from a Poisson distribution with unknown parameter? So we have in our hand a Poisson distribution with unknown parameter, and we have to check whether the data is adequate to get a Poisson parent. Consider another example. This is about a continuous random variable. Consider the heights of 100 students in a certain class in the form of a group distribution. The heights are given in the form of class intervals starting from 154 to 179. We have 5 class intervals, and the corresponding frequencies, that is the corresponding number of students, are also given. So in this case also the number of observations, which is 100, is quite large to assume normality. However, the data is presented in the form of a frequency distribution. Moreover, the distribution is height is known to be normal. But even under the assumption of normality, the parameters are not specified. So the question is how to check the observations are coming from a normal distribution. So what we get from these examples? From these examples we see that we often have data in the form of frequency distributions, either from a continuous distribution or from a discrete distribution with unspecified parameters. In each case, in any situation, the objective was to test whether a given distribution fits the data well. So we start with goodness of fit and its description and how it fits to Pearsonian chi-square statistic. Consider n observations on a random variable x. Let the range of x be divided into mutually exclusive and exhaustive sets ai, and observations are classified into these classes. Let fi be the number of observations classified in ai. Then summation I from 1 to k fi equals small n. Define pi as the probability that an x observation falls in ai under the null hypothesis. We have the hypothesis that p1 equal to p0, p2 equal to p2 0 up to pk equal to pk0, where p1 0, p2 0, pk0 are either specified by the null hypothesis or not specified. So we want to test the hypothesis that P1 equal to P1 naught, P2 equal to P2 naught up to Pk equal to Pk naught, where the Pk naught, P1 naught, P2 naught are either specified by the null hypothesis or not specified. So we start with the fact, consider the situation when PIs are completely specified. Then the joint distribution of f1, f2 up to fk minus 1 is k minus 1 variate multinomial with parameters n, p1 up to pk minus 1. Then under the null hypothesis, fi are expected to be closer to npi for each I. Then departure from the null hypothesis can be measured by Pearson's chi-square statistic Tn, which is summation I from 1 to k fi minus npi whole square divided by npi. Now the higher is the discrepancy, the larger is the value of Tn, and hence a higher value indicates departure from the null hypothesis. Since under the null hypothesis uk, that is summation I from 1 to k fi minus npi naught whole square divided by npi naught converges in distribution to a chi-square variable with k minus 1 degrees of freedom, a large sample test rejects the null hypothesis if this uk exceeds the upper alpha percentage points of a chi-square variable with k minus 1 degrees of freedom. We have just seen how Pearson's chi-square is important in statistical literature. We have seen how to obtain the large sample distribution when we have some frequency, and we have also discussed one such application of Pearson's chi-square statistic, that is goodness of fit test, when all the parameters are specified under the null hypothesis. But often the parameters are not all specified under the null hypothesis, and in our next module we shall start with such a scenario. Then we pass on to our next applications of chi-square statistic, namely test for association and test for homogeneity, and then we shall discuss Yates continuity correction. And in the next part of our next module we shall discuss large sample optimality of estimators, that is asymptotic relative efficiency and consistency in the context of estimation of parameters.